So we're honored to have Professor Tomohiro Tachi here today, visiting from University of Tokyo. We first met in SIGGRAPH 2006, which was in Boston, big graphics conference, and when he was a PhD student. And Tomohiro has very quickly become a star in the area of computational origami. And it's really exciting to see, in particular, his perspective coming from an architecture background and how that influences his work. He's going to talk about lots of exciting things in the context of architectural origami for our grand finale lecture. So please welcome Tomohiro.
Thank you very much, Eric. I'm Tomohiro Tachi from the University of Tokyo, and I'm going to talk about architecture origami, which is architecture form design systems based on computational origami. So first, introduction. So I have been doing origami as hobby as well as my research. Well, it was before my research started that I began folding. So these are examples of folding using kind of traditional way of box pleating or a 3D curve surface. So this is kind of pure origami. And there is also applied origami, which is applying origami for engineering purposes. For example, we can use sheet folding for manufacturing a 3D surface, or use it for increasing the structural stiffness. And these are examples of formed 3D surface from a sheet of metal. We can use dynamic property of origami for deployable structure, or such as this is folding of solar panels and used for special structures. And good thing about origami is that unlike the truss structure or scissors structure, you can form basically a continuous surface, and that continuity is preserved all the way of the transformation. So this makes origami potentially useful for adaptive environment, which includes context customized design or personal design, so that you can make some kind of origami structures that fit into customized to your body or customized to the design context. And you can, of course, do fabrication-oriented design, so that you can efficiently use the material and to build the 3D structure that you want. So what I'm proposing with the architecture origami is, so it's different from origami architecture. Well, I have been using origami architecture, the word origami architecture, which might mean that kind of application of origami to design. And so in that way, design, so this is the direction of application. So we start from some kind of shape or pattern and see how it is folded, or see the behavior by simulating or directly applying in physical world. But that can result in kind of very restricted design because origami is very constrained, and that will just result in just a copy of some known origami pattern to design. Or sometimes there are lots of origami-inspired design that doesn't use any of the origami properties that might be useful for engineering purpose. So what I am proposing with the word architecture origami is that origami theory for design and design system that uses that. So the idea is in this direction. So we want to get some kind of designed property, like how it behaves in 3D or in time also. And we are going to characterize the, we want to extract the characteristics of origami and obtain the solution from the that required condition, and also design context that are given by the design purpose. So this is the outline. First is Origamizer. So I'm going to talk about the basically the softwares I've been developing, the systems. One is Origamizer. So this is some of you have attended Eric's class and saw the theoretic side of the Origamizer algorithm. But I'm going to talk about the software itself that and the algorithm that efficiently works. So first, Origamizer. So this software is available on my webpage. It's freely available. So it's about origami design. So this is my oldest work as a research. We had tree method or circle river method, circle river packing method developed by Meguro and Lang, which is using tree figure, stick figure for representing the model, and design that by packing circles and rivers. That's, I think, Jason has talked in the class. So this is existing method for origami design. And what I wanted to do is make 3D instead of this kind of 1D figure. So this is what we can get from the circle river packing method. And with Origamizer or freeform origami, we can get this kind of 3D form. And you can say that what you see is what you fold. So in this, yeah, yes. So in this case, what you see is not what you fold, actually. Anyway, so I did manually design something like that. It's a laptop PC. Well, I think it's the most complicated one. So for example, you can see there is RGB output here and USB outputs here. And this is the touchpad and this is keyboards. And good thing about that is the function key is a little bit narrower than the normal key here. Anyway, this is what I've been working as. Well, I think it was like my hobby, but I was trying to make some kind of box splitting to make anything. So, and also this is more three-dimensional figure, like that. That the body is represented by basically by blocks of cubes. And I did more purely geometric thing with concave vertex. So this was very important for me. There are it's very easy to make convex polyhedron with paper. Just wrapping paper will result in the folding. But it's very hard to make concave vertex. So when I finished this model, I thought everything is possible. So I did a software to do this for me. So the problem is to realize arbitrarily given polyhedral surface with a developable surface by folding. And the geometric constraint is, of course, developability, so that it can be folded from a sheet of paper. And in this case, we forget about continuous motion from a sheet of paper to the resulting state. We believe that it exists, and physically it exists. So it works. And it can be applied in engineering sense for fabrication by folding and bending. So we put arbitrary polyhedron and get the crease pattern and you, by only folding this point, you get the folded state that's the same as this arbitrarily given polyhedron. So the idea is to use tuck. This is a given polyhedron, and this gray area is our tucks. And by folding the tuck, it's hidden. It's flat folded, and it's hidden behind a polyhedral surface, like in this movie. And when it's in developed state, it forms a plane with a surface polyhedron. So this is good because we can make a negative curvature vertex, concave or negative curvature vertex. So the basic idea, the basic algorithm, is to start from making the problem into layouting the surface polygons onto a plane. And by properly aligning, we can get the edge tucking molecule that folds the edge to edge, and vertex tucking molecule which folds vertex to vertex, vertices to vertex, and we can pack them and tessellate the surface with these elements. And we can parameterize this configuration, and we can solve it by solving non-linear equation and inequality conditions. So that's the basic idea. What we have is geometric constraints which are represented by equations. So these are the equations where this one represents the total sum sums up to 2 pi, and this shows that this forms a closed loop for each vertex. And we assign these conditions for each vertex, and we solve that by two-step linear mapping, which is basically solving this equation and these equations. Good thing about that is that it becomes linear, and which means that you can pre-compute, and you get the you can go around the solution space. I will show you later the simulation system, the design system. These are inequality conditions, which are sorry about this Japanese, but I think, well, I don't go into details, but there are several inequality conditions which are for making crease pattern and for making it to fit into 3D configuration of the polyhedron and tuck proxy, which is assumed place of the tuck that's hidden. So this is a system. So this is, you put the input here in this window, and you have the layout of the polygon, surface polygons, and then you get the crease pattern like that. So it automatically generates the crease pattern. And here you see it's edited in real time. This is, by the way, this is real time. And so it's using that the linear equations are represented by linear equations. So you can solve, pre-compute the linear matrix, and then you can calculate the configuration interactively. And you can also do some kind of boundary editing. Do you have a question?
Yes. Does this maximize the amount of paper on the outside?
So it's about the maximizing the size of the model with respect to the paper size. It's not.
So that would be a quadratic program.
Yes, you can, of course, implement some kind of optimization onto the program, but I keep it more free so that the software user can search within the solution space that satisfies these organizing conditions. So this is a series of results that are folded. And so this is how to fold the origami bunny. So first thing you do is to get crease pattern using Origamizer, and then fold along the given crease pattern like this. Interesting thing about that is that it's changing the lighting condition. It starts from natural light and it becomes into artificial light. It takes about 10 hours or something. And it's done. And I have this one.
How many have you folded?
There are 2 existing models, not one, so it's very easy to reproduce. So, so one thing that we are doing is I'm doing with Eric is to prove that anything is possible. So the software is a little bit, what do you say, approximation, or it doesn't work in some cases. So we are doing on really make it possible. So this is the part of the Origamizer. So if you have questions for Origamizer, yes?
So for the input of the model that you're trying to use, is it a wavefront? Is it the format? Is it like
it's like polygons.
What's the file format that you have to import in order to?
Format of 3D input. It's basically OBJ file that this accepts. This particular software accepts, but basically it's okay if it's polyhedral surface with actually any topology, because you can basically assign the boundary of paper onto it so that it always becomes a disk. Yes?
You mentioned that early on in the process, you need to properly lay out the polygons onto a plane. What constitutes proper layout?
So your question is, what is a proper layout? I mean, so this is basically given by these conditions. In intuitive way, if you lay out polygons, I want to fold this line onto this line, so that with actually a single line. So you have to keep this symmetric against some line. So that gives a constraint. Also, this is the basic equations that you have to solve. And there are several others, such as the boundary should be convex, because we don't want to end up in some kind of very complex boundary. And if it's foldable from a convex paper, then it's foldable from a square. So that's the convexity of paper. No intersection between, of course, between polygons. And it's a little bit difficult, but when you place crease lines, then it might hit adjacent crease lines. That's pretty bad, so you have to avoid that. Also, you have to fit to the 3D surface, and sometimes the tuck that coming inside is bad, so you have to adjust that. And in order to do that, you need a condition.
So do you find that you're moving around where the edges of the beam end up on the model, or can you just start anywhere and reasonably come up with a solution?
So it's how to solve.
Yeah, does it get a lot harder as the model
Mm-hmm.
as the polygons increase, or?
So it's not by step-by-step approach to laying out one piece at a time, but it's more like solving all the equations all at the same time using big vector equation.
Maybe what it means is it numerically well conditioned?
No. So that's why we need extra work for proving.
That it's always full rank.
So that's a question. Well, it's not always. So there are some times that produces some kind of over-constrained part and free part.
Also, are the tucks under mechanical tension? Does it want to stay tucked, or does it want to come apart?
Physical property of the tuck.
Yes.
So because of the crimping that are done to each of these vertices to fit the curvature, it stays in this form. Like you don't have any glues or clips here. So this is actually a good property of this design method. Yes.
Because you're to approximate a curve, you're breaking it down into smaller straight lines, straight edge segments. Is that user definable as to what the lower bound is to how granular you make the curve approximation?
So about the condition for the input is, so in this system I don't give any kind of numerical boundary, upper boundary for the regularity of triangles or something. So well, but I think it's good if we can do for anything. So that's why I'm working on with Eric on proving. So that's okay.
Is there a Mac version of
Mac version. No, it's still Windows version only. But well, it's written with cross-platform libraries. So yes. So sometime in future. Okay. So let's move on to the next topic and software, which is freeform origami. So the objective of the freeform origami is that we want to be more. We don't want to spend too much time to make this kind of 3D forms. So, and also we want some kind of conditions, not only developability. We want some condition that's that most origami has. This is flat foldability, so that it falls flat, and also transformability or kind of elastic properties. So we want to use these kind of good properties from origami while we want to make some kind of freeform surface. So the approach here is start from existing origami models and then modify that to a different shape while keeping the origami conditions with direct, straightforward user interface. Here, I use triangular mesh for representing the origami model, and we represent the origami models by the vertex coordinates of the model. And these variables are constrained by developability and foldability, flat foldability. So this is a very direct way of implementing origami deformation. So first thing we want to keep is developability, which is that you can fold from a sheet of paper. Globally, so in engineering sense, it means that it can be manufactured from a sheet material, which is very nice, by folding and bending only. And the condition is globally represented that there exists some isometric mapping to a plane. But if the surface is a topological disk, it can be represented by local condition that of every point. That so every point on the surface, the Gauss curvature is 0. Actually, we are thinking of non-smooth surface, but we are thinking of piecewise linear surface, which allows variation. So smooth developable surface is only allowed to be in these forms, but we have lots of different form variations for if we allow creases. So we have to, even in this case, we have to think about Gauss area. And it's very easy to define Gauss area for a C2 version of surface by using curvatures, multiplying curvatures. But for Polyhedra case, we use instead Gauss area, which is represented by the this, which is 2 pi minus sum of angles around the vertex. So, well, it's very simple way to express that it's folded from a plane. So this sums up to 2 pi. So this is what you can use for developability. We want to also have flat foldability for the surface. So this is applicable for compactly packaging surface. So from 3D to 2D and from 2D to 3D. And it's also represented by isometric condition, like in developability. And also we have a little bit of layering condition, which is actually NP complete, so which is hard. But for practical purpose, we can avoid that. So first one is isometry, so that that can be similarly represented by angle condition, which is called Kawasaki theorem, so that the alternating sum of each vertex is 0, and the layer ordering is NP complete, but we can use for some, for example, a sufficient condition given by Kawasaki, or empirical condition, which are basically given for each local adjacent angles, so it's very easy to implement. And it works, so we forget about NP complete part. And also, we can give several constraints. For example, this fold doesn't want to fold so that it forms a planar surface, or you can fix the point to some space, a point in 3D space, or we can make some point, some edge to be rigid. So we have these coordinates, and these are the variables to represent the configuration. And we assign developability, flat foldability, or other constraints. And within the, this forms an underdetermined system So which means that it gives you a multi-dimensional solution space. And within the solution space, we transform the surface so that then you will get the always valid solution. So that's the method we are applying. In order to solve that, we can use the Jacobian of the constraints and calculate it numerically. So for each step, it's a given assumed transformation mode, and this gives you a valid transformation mode by using the generalized inverse or pseudo-inverse. And you can implement into a software like this. So this is what happens. The top is what happens with freeform origami. So this is a crease pattern of the paper, and this is a folded pattern when it's X-rayed. So you can see that if you drag this point up, then all the crease pattern and the flat folded pattern changes at the same time. This is for comparison. This is kind of a simulation. So in this case, the model cannot change the crease pattern, and which makes a less flexible motion for origami. Also, we want to do some mesh modification by because if you move if you change the crease pattern, then it will end up in degenerate triangles, so that we need to do some kind of edge collapse operation. However, in order to do that, we have several conditions. We have to keep Michaelis theorem if the surface is flat foldable, and we use that for doing edge collapsing and mesh modification. So if you see these patterns change, and these are getting very degenerate triangles, and that are removed by this operation. So this is interesting because you will end up in different patterns with similar. This part is kind of similar to diamond pattern or Yoshimura pattern, and this part is kept the same as Miuraori pattern. So mesh modification enables to transform to produce more variations for pattern. So from now on, I will show some examples of freeform origami. First one is starting from Miuraori. That's, I think it's well known. This is actually very old. You can see from napkin folds. And for paper models, I think you can see pictures from Bauhaus. And anyway, this is it's called Miuraori, and it gives you expansive motion, and also it can be compactly packaged, and it's developable, of course. So this is the variation of that, and this is another example. So it's this model is called melting ice cream, but the idea is that using variation of Miuraori, it forms 3D surface that is irregular and asymmetric, and while it can be folded flat, so that you can roll it up to carry out. So this is a model. Yes. This is another example. Here I wanted to start from regular Amiraori and then to transform into a more freeform surface. You can also generalize Ronrecht's pattern. This is one of Ronrecht's designed triangular tessellation. Good thing about this is that it forms a kind of a composite surface when it's folded. So it's composed with top surface and tucks inside, just like this bunny, but it's more flexible and it can fold from a sheet to the 3D form. In order to design this, we assigned the condition that in 3D state, these three vertices form one vertex. That's extra constraints to enable generalization of Ronrecht pattern. So, for example, you can get this kind of asymmetric polyhedra surface with this generalized pattern, or this form with this pattern. So each triangle has different shapes, a little bit of differentiated shape. Or you can just apply to some regular triangular mesh and then get some nice crumpled paper like that. So I think this is a good way for using this software. So you can design crumpled paper so that it's very hard to crumple paper in real life. If you feel it's very difficult, then you can use this software to crumple paper. This is a generalized version of Yoshimura pattern or diamond pattern that you can use for a kind of shell-like structure. This is another pattern called water bomb pattern, where interesting. Yes, it's supposed to be playing the pufferfish motion by Sippo. Anyway, this type of pattern is called water bomb pattern. I think it's the oldest known is by Shuzo Fujimoto. So it's kind of flexible pattern, and because it's flat foldable, it can be used for deployable structure, and it's because of the elastic property that the folding gives, you can use for texture material or kind of cloth folding. Anyway, this is an example of deformation. So this is the normal water bomb pattern that's based on triangles. And this one forms more planar surface when it's in 3D. And this is some generalization. This is the folded form. I think it's a little bit too small to show. So this is the thing, the pattern, and you fold it into a kind of a butterfly shape, and it forms a hyperbolic paraboloidal shape, but it's a saddle shape. So this is another way to make a hyper in paper, and this exists. So this was freeform origami. Do you have any questions about freeform origami?
Why can't you solve directly for the final shape that you want?
The question is, why do I not search for the 3D shape instead of gradually changing? This is because the constraints are nonlinear, and that makes it possible that the solution doesn't exist. But if you do it continuously, then it is always true that you get the right answer. And I wanted to make it one of the reasons I wanted to do this is that so this is a demonstration. So this is good because basically you can interact with the geometry of origami to find some new results. So so it's more similar to when you design with paper, like when you interact with real material. But this gives more flexible change of material than simulation. And I wanted to make that kind of interaction possible. So this moves like that. And that changes the pattern. So that's the reason I do it in this way, solve the equation by deformation. Any question?
I'm just curious, how long did it take you to develop both this and the Origamizer program?
The time for developing the softwares. Well, it's always continuing. I'm always continuing developing, so it's very hard to say. But I think, I don't know. I think basically it starts to work in half a year and then polish a lot of times.
Did you want to show the metal one?
Yeah. No, not yet. Yes. Not yet. Okay. So then we talk about the rigid origami. Oh, question. Question.
I might not understand it correctly, but in either of these programs, or is there a program that exists that allows the user to design dynamically like this curved crease origami?
So curved crease origami is quite hard. I have tried with this software, and it works for some cases, and it doesn't work for most of the cases because of the because there are too much degrees of freedom. Because if you simulate curve folding by kind of quadrilateral strip, very thin quadrilateral strips, and so that's future work, so that the software can work with curve folding. If it's a coarse approximation, then it works. So, rigid origami. So this is this is the closest part of computational origami that's to architecture. And so rigid origami is plates and hinges model for origami. And like this. So each rigid panel is connected by adjacent connected to adjacent panel with rotational hinge, one-axis hinge. And the panels do not deform, and it produces synchronized motion. So that's a model when you want to apply origami's dynamic features to some designs. And this is a kind of comparison, and this illustrates the energy strain energy that's caused by the distortion of facets. So, for example, this model falls to this state, but there is no path that gives you zero energy deformation. But this is rigid foldable, which is which keeps each of the facet not deforming. And it's useful for self-deployable structure or architectural structure that is very large. You can substitute panels with thick panels. I will talk in the last part. So like this. So here, so rigid origami. Oops. Here we want to apply rigid origami to design purposes. In order to do that, we want to think about first to also generalize rigid foldability to different shapes, and also to generalize into cylinders and other topology of like compound structures. So first thing is, before that, I would like to show example of rigid folding. So this is the simulation of folding.
Could you play the lower left again?
So this is a triangulated model of a tessellation designed by Ray Champ. This is a waterborne tessellation. Okay. So first thing we want to do is to simulate folding to understand the geometry, the kinematics of rigid origami. And this is this can be represented. First easy representation is a truss model, which you basically use vertex coordinates as the variables and then constrain them with rigid bars that are connected the vertices. And this one is different representation that uses folding angle. So this is more direct way, and I have a software called Rigid Origami Simulator, which basically is based on this constraint and representation. So the configuration is represented by folding angles. And then the folding angles are constrained at each vertex by this equation, which is matrix form, 3x3 matrix form, which actually gives 9 equations, but only 3 of them are independent. So we can use 3 equations. We have 3 equations for each vertex. And that will give also underdetermined system so that you can simulate folding using also generalized inverse, so that you can search within the solution space by giving this is kind of a force that's asserted to each of the edge, and then this results in the deformation that is valid. And in generic case, because there are 3 constraints for each vertex and 1 variable for each edge, we have this degree of freedom. And first way to design rigid origami is to use this information. And from the Euler's polyhedral formula, we can say that any triangular mesh, well, not any, it's a generic triangular mesh, produces degree of freedom, which is number of edges on the boundary minus 3. So, for example, in this hyper triangular model, this gives 1 degree of freedom because the boundary edges are 4. And we can generalize it to cases where there are holes also. And with this idea, you can make hexagonal tripod shell, which is using 6 edge, so hexagonal boundary, so that the degree of freedom is 3. And then we pin joint 3 of the vertices, which gives 9 constraints. And because of the rigid body degree of freedom, which is 6, we have 9 degrees of freedom for of transformation, and then that are constrained by 9, so it produces static structure. And by changing the position of these points, you can get the different forms. So, for example, this is the shape, triangular form that the position of this pod changes the overall shape, and it's static when it's fixed. It's all pin joint. So this is an example. So if you change the position of the leg, then you get the different shapes for 3D configuration, like this. So this is one way to build rigid origami structures. This is quite, what do you say? Oops. Obvious result. It's theoretically it's more interesting to think about the one that you cannot imagine the transformation. For example, quadrilateral mesh. So for quadrilateral mesh, each vertex has also 3 constraints, so that this itself forms a 1DOF structure. Think about when you form a mesh with this, like Miraori. So basically, if you define this folding angle, then all the folding angles here are defined. If you have another vertex, degree for vertex, then everything is here defined. And you want to have another vertex here that is defined by this folding angle. And then you will have a problem here because this folding angle and this folding angle contradicts in general, well, in general, there is it contradicts so that you cannot make an array of folding by quadrilateral mesh. However, as you can see from this figure, there exists examples like Miraori that gives 1 degree of freedom motion. This is actually very interesting thing happening. And also this is great because all the constraints are redundant. You can remove this part, so you can put a hole in the center, but still it results in the same motion. And you can improve, you can design more freely with this kind of robust redundant constraint structure. So what I want to do is to generalize this to more to free form. And we start from Miraori and also start from this pattern, which is not a developable surface, but also gives 1 degree of freedom motion with redundant constraints and its quadrilateral mesh design. So this can be generalized to rigid non-symmetric forms. So Miraori is something like that, and we can extract the property of rigid folding by looking at these vertex. So if it's a flat foldable vertex, it's a 4 vertex with flat foldability. And this gives folding motion where the opposite folding angle are same and these are same, and also that the folding angle here and here are related. If you look at tangent of half of the angle, then it's linearly related. This is very useful, and because if you find one configuration that works, then you will have continuous folding that works. Anyway, in this way, you can make sufficient condition for making quadrilateral mesh rigid foldable. And this is easy to get because the finite folding motion, so the continuous folding motion from a sheet to the folded state is guaranteed by one 3D configuration that satisfies these conditions. And in order to get one configuration that satisfies this configuration, we can use the freeform origami. So it's very easy for us to do that. And this is an example of rigid origami that's using redundant constraints. So it produces 1 degree of freedom motion. And it's very light because this part and this part counterbalances the gravity. Oh, this is another example. So quadrilateral mesh can be a rigid folding motion. Well, you can apply to something like curve folding. It's rigid foldable curve folding. This is kind of contradictory, but we can rationalize curve folding into quadrilateral mesh. Then you can do produce 1 degree of freedom motion like that. Another example with thickness is here. So it's interesting that it produces folding. It's 1 degree of freedom motion, so that every motion is kind of coded in the pattern here. So another example is using egg box pattern, and this actually has the same property as the mirror or vertex or flat foldable degree for vertex, and so that you can use the same idea to produce rigid foldable variations. And you can actually combine with origami structure if you define this mountain fold, valley fold, and also add complementary mountain fold and complementary valley fold defined by the defined here. If you use that kind of extension of the origami, then you will get, I think I will skip this part, but you will get design variations that combines origami. This part is origami vertex, but this is not. So this can have positive Gaussian curvature, while this part is 0 Gaussian curvature. And you can, it's interesting point is that you can define developed and flat folded state, or actually in this case, it's 2 flat folded states, because in this case, it's not totally open. It's not totally developed, but complementary fold lines are folded. So anyway, so that's why I call it bidirectionally flat foldable planar quadrilateral mesh. And that can be rigidly foldable. So this is an example. Okay. Oops. What's happening? Okay. So this was about a disk, and we can develop into a cylindrical structure. And cylinder is not trivial, because, for example, if you think this is non-origami pattern, but this doesn't transform to this pattern because this is different. This has different number of edges. So you cannot produce this kind of motion in rigid folding mechanism. And you can see what's the problem by looking at this kind of disk surface that is rigidly foldable, and it forms a cylinder in at one state, but it doesn't produce in a continuous motion that fix this loop. But there exists. So the idea is to mirror reflect one part of Miuraori vertex. And this is actually, you can see from the origami model by Toki Yen. It's called flip-flop. It's very interesting model. Anyway, and you can develop more generalized origami cylinders like this. And I think this is rigid foldable cylinders. And since it's using quadrilateral panels, it's similarly produce 1 degree of freedom motion. And you can see, for example, like that. This is the motion produced. So any part produces the whole motion. And also you can make some kind of design variations. This is using grasshopper on rhinoceros. This is the given shape, the section, and from the section you can make kind of rigid foldable cylinder, and also composite structures like this. Or so we can make composite structures like this. So it's great that it fills the space while so it tessellates while preserving the 1 degree of freedom motion. Or this is implementation with thick panels. I think I have got a cylindrical tessellation model. So this is a tessellated model which moves like that. So it's kind of a volume that flattens into two states, and it's good that it's rigidly foldable, and it's 1 degree of freedom mechanism. So, and I want to generalize more. So this is this is symmetric. There exists one axis that repeats the unit structure. I want to make it more general. I like the asymmetry than symmetry. I think you do. Also, but you have to think about the conditions around a hole, and actually, this is difficult condition to be solved than the disk version. However, you can do that by fixing the first loop. Then you know that this part is rigid foldable, so you can continue the formation from there. So this is kind of sufficient condition, but useful for designing something like this. So it's more freeform. For example, like this is also 1 degree of freedom, rigid foldable cylinder. This is a example folded. So it folds like that. Oops. This is also an example. This forms a torus when it's folded, unfolded, probably. Or this type of structure. So it's also cylindrical. And for kind of architectural image. So this is a rigid origami for cylinder, and we can move on to the how to implement rigid origami to real model, because in architecture we want in architecture design or any other designs we want some kind of finite thickness model. There is no ideal origami. Well, probably Origami though can produce, but anyway. So we want some thickness, thick panels and rotating hinges to produce rigid origami. This is a typical way to do that. So you put the hinge on the valley side. The main problem of this one is that each vertex, this fold line is, there are several fold lines that are joining at vertex, but this will no longer be concurrent. So, but rigid origami mechanism assumes that the fold lines are concurrent, which means that if it includes translation constraints, and it increases the number of constraints for each vertex. So it was previously 3 constraints there, but it becomes 6 constraints because it includes transformation, which is very bad But there is a symmetric vertex that allows that. So using a symmetry, you can make something like that. Also, there is a way that you can slide the hinge like that. But there is a problem in the case like this. So the problem of sliding is in global accumulation of errors. So what I do is, instead of shifting hinge, you can do trim the volume of the vertex valley side of the model. And this is actually very easy. So you assume that this falls to pi minus delta, and you will get you can just remove this part according to this folding angle, maximum folding angle. And you can do that, define this point by offsetting the edges, which is basically calculating weight straight skeleton. And this is also can be applied to constant thickness panels, which is more easy to be manufactured only with 3-axis milling machine. Anyway, this is a thick panel, thick rigid origami using this method. Or this is an example using constant thickness model where no error is accumulated, like this model, slidable hinge. This is implemented by using Grasshopper again. Grasshopper is a good tool to implement something that does not require iterative optimization calculation. But it's very good for forward calculation of geometry. And that calculates the pattern, and then you can lay out the pattern. This is a cloth, and we put the thick panels on both sides of the cloth to make a rigid foldable structure like this. So in the center, there is a cloth that represents the ideal origami. So this is what happens. Okay, and I would like to give an example of rigid origami design for architecture. So this example is that we are given with existing building openings, and we want to connect these openings temporarily, and I want that to be compactly folded to fit to this facade. But because this is quite large, like that, you cannot make from a flexible material. That will be a problem if you make it as a structure. So in order to solve that kind of problem, we can use freeform origami to design to fit the condition. So these red lines are the openings of two buildings that are actually not parallel, and the sizes are different. But still, you can connect it on freeform origami, and also you can keep the boundary to fit on the ground, and then you can get these form variations, and you can choose one of them and calculate the paneling patterns, and then you can make this is rendering representation, but basically you can make this kind of structure that can connect to buildings. Okay. Thank you very much.
With the metal table.
This was more, what do you say, handcraft thing. I did this with Dukes there, and we wanted to test the metal folding, whether it's possible to be used for, whether curve folding is useful for manufacturing things. I think that's true, but this model was this model required a lot of hammering, and it wasn't so easy. But I think you can make have a way to make it more easily constructed. So this is a table with just by folding sheet of metal or chair, anything that's this one. So this one is combination of 4 papers. So it's in this case I do not restrict to be foldable from 1 sheet of paper. Well, for design, I do not do that. So you can only find it by simulating and see the collision. But basically, there will be no local condition, no local collision for this quadrilateral mesh. But there might be some global collision where this and this part are colliding.
For example, for run-rich pattern.
Run-rich pattern, I only do local collision test, which is between facets that are adjacent, which still works for that kind of good model. So, yes, I brought, I think I will show all of the things here, like that.
Any other questions? All right, thanks
Okay.
again.
Thank you very much.